Wonderful. Wish we were in Argentina. Instead, I'm in my office. um, Also, Sylvia, could you let me know about 5 minutes before the 25? Just so, yeah, that'll help me. Um, okay, so what I'm going to talk about today is actually measuring the size of band gaps in photonic crystals uh, based on the difference in material properties of the dielectric materials, the geometry of the configurations, um, and two other spectral parameters, one related to the Dirichlet spectra of the particles themselves, and the other one related to a best called a structural spectra. And with that, we can then uh, provide explicit estimate for band gap size in photonic crystals made in a certain way. Um, Without further ado, I'll go to the next slide. And maybe I don't have a slideshow, so what happened here? How do I advance? Let's see. Yeah, there we go. So this is joint work with Robert Feider, who'll be speaking later, actually, in this symposium on a harder problem, actually, more technical, in that it's in conjunction with Sylvia, actually. But this appeared in 2016 and 2017. Um, and so we'll consider Maxwell's equations for the electromagnetic field, which is composed of the electric field and the magnetic field. The electric field is calligraphy vector E there. The magnetic field is H, or actually B, and then H is the H field. And so here we have written it in its notation. Here I haven't put boundary conditions. We'll assume that H and E are L infinity, L2 on the whole R3, or in this case R2, but especially we'll specialize to R2, but for the moment R3. And omega is the frequency. Well, we don't have frequency just yet, but we have electric permittivity, which is the epsilon, which is a material constant, takes different values in different materials. And then the magnetic permeability, which is denoted here in the equation 1c as mu, which is the same for all materials. So, and when you are non-magnetic, mu is if you divide out by the free space value of the permeability, mu is 1 in both of the materials. So that's a hypothesis we will take in this for this treatment, is that mu will be the same for both materials, but that the permittivity can change between materials. And so what we'll do with the Maxwell equation is we'll go ahead and assume time harmonic solutions. So they're of a special time dependence, the usual time harmonic. And of course, the time harmonic solutions are building blocks, for Fourier. We can take inverse Fourier transforms of them, or Fourier transforms of them, and make any field we want, or pulse shape, electromagnetic pulse shape that we like. But we'll assume time harmonics. So E, a constant in time, depending on space, and multiplying the E I omega t. We plug them into Maxwell's equations. We factor out the I omega t, and we get what are called the time harmonic Maxwell equations, given by 2 through A through D. Okay. And again, I've written there, now we have a frequency. And then we have our magnetic permeability, which is the same in both materials, and then the permittivity that can change. So that's the system of equations we're going to work with. And what we're interested is, in particular, material continuum made out of two different dielectric materials. So epsilon will take on two different values. And so that's what we're going to look at. And in particular, what we're going to look at is, this is sort of looking into a plane. These are prismatic. You could think of these as P1 through P6 as the cross section of infinitely long prismatic rods. and we're looking at the plane transverse to them, and this is their cross sections. And in the rod, the dielectric permittivity will be unity, so it'll be 1 in the orange shapes there, in the orange cross sections, and it will be K, where K is going to be taken to be quite large, in the M, which is very short for matrix. So 1 value in the P domains, P1 through 6, given by 1, and then K in the connected phase surrounding. So all of these particles will be separated. There's no touching here. So everything is separated by some minimum distance, as you can see here. Okay, so that's what the geometry we're going to consider is. So it's really going to be constant geometry coming out of the screen, and then you'll have all your variation within the screen. Okay, so because of that geometrical consideration, we're going to consider what are called transverse electric fields, meaning that the electric field will be in the plane transverse to the rods, and the magnetic field will be parallel to the generators of the rods. And so what we can do is we can actually solve for the H, or the magnetic field. Since it is non-magnetic, we just have the B field is equal to the H field. And so what we're going to do is we'll solve from the H field, and the H field, which we call H of Z, is just directed out of the screen. And so it's in the E3 direction. So E3 will be the unit vector pointing out of the screen. E1 and E2 will be unit vectors in the screen. Little h is the H field there. And so what we ask, if we know what the H field is for this particular geometry, then we can quickly solve for the E field, and that's the electric field in the transverse plane. It's uniform in the X3 variable. And so in the X1, X2 variables, the E field is given in terms of the curl of the H field. And then prefactor there is I times C divided by the frequency times, and then epsilon K, which is the permittivity that takes the value 1 in between the particles and the value, takes the value K in between the particles and the value 1 in the particle. So Maxwell's equations then reduce to finding the unknown H, little h. And the unknown little h, just substitute variables, the Maxwell equation collapses and becomes just a scalar equation for H. And it's a very familiar Helmholtz equation that you see there in equation number 4. The frequency appears there now squared. And so what we'd like to do is we'd like to consider what are well-known solutions called the block wave solutions. So basically, those are the form H below there, where H is given by a periodic function phi, periodic in X, times this exponential, which is alpha, which is a vector in what is called the first Brillouin zone. And here, that's Y star. And so that is a block wave solution to 4. Of course, we have to find a pair. We have to find an H and an omega at the same time. So we want to find it's an eigenvalue problem. So we want to find a pair for the existence of solutions. So the 4 exists. The solution of simultaneous, we have to find an omega and an H such that 4 exists. And we would like to do that for every alpha in the Brillouin zone, if possible. And if not possible, if we can find one for every alpha in the first Brillouin zone, we call it a band gap. So now remember that if we want to, the H is the one factor of the time harmonic solution, and in this way we can figure out frequencies in which there exist time harmonic solutions that could exist inside this photonic crystal. And if in fact there's a band gap, then that is for every choice of alpha, we just cannot find an eigenvalue eigenfunction pair, then nothing can propagate in that crystal. And that's of physical interest and of technological interest too. because you can introduce a defect into a material, a certain frequency with band gap, and all kinds of fun can happen. You can have long wave propagation of signals. There's many technological things you can do. So just to summarize, the pair H omega is said to be a solution of the block eigenvalue problem for alpha in the first Brillouin zone. And the fact is that it's well known from theory that for real K, the block eigenvalue in the first Brillouin, here K is the dielectric property in between the particles. Okay, and so for real K, it's known that the block eigenvalues are a finite multiplicity for each alpha in the first Brillouin zone. And then the dispersion relation, the second bullet there, is the frequency is related to alpha, and K is actually the first, is the dispersion relation that we're seeking. So when the frequency is related to the first, this eigenvalue lambda j, then we actually have a block wave propagating through at parameter alpha, which is basically the direction of the block wave. And so j gives us, so we have a continuous spectra. So for each j, we run through all alphas and y star, and then we take the next branch, which is the next value of j, et cetera. So the band structure can be quite complicated, but what we're seeking is when we have a band gap. And so before I get there, I'll just say, so when we do satisfy the dispersion relation, then we do have, is in equation 5, a propagating magnetic field. In here, I've written the time harmonic form completely. And again, kappa is the direction of traveling wave. And you can see here, kappa is just the unit value written in polar coordinates of alpha in the first Brillouin zone. And the magnitude of the wave number is the magnitude of alpha. And then, so we have our H, and then we can find our E. Okay, now here's the thing again. If there's an interval of frequencies, omega minus, omega plus, and omega is in that interval, for which we cannot find any propagating wave, time harmonic wave of this block wave form, for every choice of alpha in the first Brillouin zone, there's just no, then we call that interval a band gap. That is there's just no waves propagating in the crystal for those frequencies along any direction. And the physical mechanism behind all of this is multiple diffraction off the scatterers. So what we would like to do is understand when that could occur. When that could occur. So to fix ideas, I'll just put in one scatter in our unit cell. It's easier to think of it that way. And what's going to be very interesting here is the Dirichlet spectra of the domain P. So the Dirichlet eigenvalues. Okay, that's going to play a huge part in understanding this. So here's what happens. And this was sorted out by Hempel and Linnell using some very nice convergence results for quadratic forms, and as well as the min-max formulation for eigenvalues, and a very simple mechanism. And what they find is that as the dielectric permittivity of the connected phase goes to infinity, we get a limit. And here's the generic picture of the limit. What happens when k equals infinity, and what happens as k is near infinity? Okay, so I'm going to give you the generic picture of what happens when k is infinity, and then I'm going to back away and say, well, let's just take k to be a neighborhood of infinity, and what is going on. And so the generic picture is the following. The limit spectrum, when you take k to infinity and equals infinity, the limit spectra is no longer parameterized by alpha, and instead is just of the form is characterized by the Dirichlet eigenvalues of P. That's it. So that's very nice. I mean, there's a separation, everything sorts itself out. And so what I've done here is I've shown this interlacing, delta 1, nu 2, delta 2, nu 2. And there's a slight difference between delta 1 and the deltas and the nus. I'll get to that in a minute, but they're all Dirichlet. Well, almost all of them are Dirichlet eigenvalues. Not all the nus are Dirichlet eigenvalues. The key point of Hempel now is in a neighborhood of infinity. So K isn't equal to infinite. There is an epsilon. There exists an epsilon such that the spectra around these limiting Dirichlet eigenvalues, these special Dirichlet eigenvalues, which I'll talk about in a minute, is characterized in the following way. Between nu j, which is a Dirichlet eigenvalue, and it's the next greatest Dirichlet eigenvalue, delta star, if we take away a little bit of, which is delta star minus epsilon, we'll have a band in there. That will be a subset of the band. On the other hand, if you look at delta star and the next special eigenvalue above it, and you take away a little bit from that, you'll have a band gap. And they show that this is generic. And so the question we had was when we looked at it, we said, well, is it possible to say what epsilon is? That is, can we say, relate epsilon to the contrast? So what is the limiting contrast that we would need? Or, let's take a neighborhood of infinity. Let's figure out neighborhoods of infinity for which we have bands and band gaps that look like this figure, but say what that neighborhood of infinity looks like and characterize it. And so that's the nature of what the results I'm going to show you. So we're going to have quantitative estimates. So we're going to replace epsilon with K, okay? Or with functions of the contrast that depend on the geometry of the scatterers and various spectra associated with those scatterers. So that's the goal. And well, that's what we did. So that's what I wanted to say. So this is the motivation. Find explicit formulas for epsilon that were found by Hempel and now. Okay, so find the explicit range and contrast and size of pass bands and band gaps in terms of scatterer geometry. And so, like I said, these theoretical results, as I've stated them so far, are asymptotic. And what we would like to do is find an explicit dependence of pass bands and band gaps on K. So obviously, we need to get some information and do some digging and find out, what we need. And then if it turns out, though, we can. And we can find out, maybe there are better bounds, but we can find out bounds. And we can also determine all the band gaps. So we need to understand spectral behavior of the solution operators or the operators associated with this eigenvalue problem. And so we do that. So that's what we do. So what I'll do is I'll do a special example. So imagine we have 4 scatterers and they're buffered, meaning that the scatterers all are of the same radii, but they're buffered. There's a slightly larger disk of radii B, and no 2 scatterers could be closer together than that. Otherwise, they could be randomly placed inside the period. And then we repeat that pattern throughout the plane. Okay, so let's consider that. Okay, and I'm going to give you quantitative estimates. I'll give you a formula for epsilon. So the disk can be arranged in any configuration inside the period cell. We'll write B, the outer radii, as some value A, the actual disk size plus T. So that'll be B. And we can throw in N disks if we want. 4 is fine. And the nice thing is that for that case, the spectra, for the 4 independently connected disk, the Dirichlet spectrum is easy to write down. It's associated with a single disk of radius A. Now, the part of the spectrum associated with the Dirichlet eigenfunctions have a non-zero average over a disk, because we actually know them for a disk, and they're Bessel functions, are the Bessel functions of order 0, and they're related. So the Dirichlet eigenvalues associated with eigenfunctions that have non-zero mean are written with an asterisk on it. And these correspond to the Bessel functions of order 0, because those are eigenfunctions that have non-zero mean. They don't depend on theta. They don't depend on the azimuthal angle. We examine Dirichlet eigenvalues associated with mean zero eigenfunctions. Those are the delta stars. And, excuse me. Okay, we're going to know. We should have. That should be denoted by, okay, that new nk should be a delta 0k. So the delta 0k, and that should be a eta 0k, okay, where eta 0k is the zeroth of the zeroth Bessel function. Okay, then we introduce mean zero. Okay, no, excuse me, I'm reading the bullets wrong. The Dirichlet eigenvalue, as opposed to the mean non-zero ones, those are the delta stars, then we also look at the mean zero ones. And the mean zero ones are these new NKs. Okay, now and so, and those are associated with the nth Bessel functions for n bigger than or equal to 1. So we introduce now a spectral function, which is in terms of the eigenvalues of mean non-zero eigenfunctions. Those are the delta stars. And then the averages A0K of those eigenfunctions. Okay. And here I normalize them in equation 9. And so then what I can do is I can write down the spectrum sigma n, which is the union of the zeros of the spectral function. Okay, so this spectral function here given in 8 has some zeros. So I look at the new's that make that function 0. Those will be the first bracket there, the union of the new 0j's. And then I'll union them with all the mean 0 Dirichlet eigenfunctions. So I write that as sigma n, and then separately I write the Dirichlet spectrum as the mean non-zero eigenfunction eigenvalues, which is the first bracket, union, all the mean 0 ones again, and that's equation 11. So I have these two things, and then we get the following. So here I'll just show the result in pictures. We get that there is a certain kj, so for the jth band, here tilde, j tilde, such that if the contrast k is bigger than that, then on the left there, you see we have a band below sigma star 0j. We'll have a band below it, and above it, adjacent to it, we have a gap. Okay, so that's what we've shown. Now I'm going to show you unpack it and show you with a k tilde. What is the k tilde? How big do you have to be in order to have this nice band and band gap? Okay, and so the answer is here. You go ahead and there is basically an element which is of the spectrum sigma n, which is closest to the mean 0 Dirichlet eigenfunction. I'll call that nu nj, and then I look and I measure all the other points close, it's closest, the closest one to nu nj of this zero eigenfunctions, mean 0 eigenfunctions. I call that dj. Fine. And then what I do is I form what is called R bar j for the jth gap. And it's basically pi squared times dj, that number, times the difference in the radii of that buffer geometry, the outer radii minus the inner radii, And then miraculously, we have our band gap estimate. That is, that 14 says that, so ideally, from the limit theory, you have a band gap between, in 14, delta asterisk 0j and nu j plus 1. So Hempel will now give you that. And then you say, well, I'm going to back away a little bit and say, hey, no, I'm not at infinity. I'm above k bar. How big is my band gap? Well, it's given by 14 explicitly, meaning it's the interval between nu j. Well, it's not quite nu j. It's nu j minus a little bit. And that minus a little bit times nu j plus 1 is the epsilon. And it's explicitly given there in terms of these spectral parameters. And in addition to the geometric parameters 13. So this is the quantitative estimate for band gap opening. And so it actually gives you a back of the envelope formula for calculating how big a band gap is analytically. So up till now, we've been doing it numerically and hoping that our numerics is right, and it is. But here's a way for a certain type of scattering geometry to get an explicit formula, which is, that's nice. And so, you know, we're looking on to maybe trying to build it and see if everything's reasonable enough and the contrasts are reasonable enough, can we build it? Then we also have the pass bands, again, replacing epsilon with now 18, which would be instead of delta sigma, I mean delta asterisk minus epsilon, it's delta asterisk minus delta asterisk times squared dj divided by kr, and we will have a pass band. Certainly that pass band will be, this interval will be a subset of a pass band, provided at k 19, that k is bigger than this k lower bar given explicitly. So these are the quantitative estimates. These are the quantitative estimates. So I was just hoping to just say this much during the lecture. Now I'll just discuss briefly, you know, the proof.
Rob, we have 2 minutes.
Beautiful. So I'm just going to say briefly the strategy of the proof, because I knew it was going to take a long time to explain the theorem. So the way we go about it is we find explicit dependence, of course, on block spectra with the contrast. To do this, what we do is we use power series. We expand the operator in a power series and apply, okay, well, I'll just say we expand in a power series, and then we basically, the way we define all these geometric parameters is just explicit formulas for the radii of convergence of that power series. And so we basically develop an explicit power series in 1 over k for these eigenvalues, and provide an explicit formula for the radius of convergence. And let's see, just if we're going to use analyticity and do power series, best thing to do is complexify. Okay, so our coupling constants in the complex plane. We get a representation formula, like I said. Aspects of this approach, I should say, there are parts of this approach which are touch upon the notion of T-coercivity introduced by Buffa, Costabile, and Schwab. And then we obtain the representation formula is then applied directly to explain explicit formulas for each term in the power series. And then we obtain radii of convergence in this power series. So with that, I'll just go ahead and stop. And thank you very much.
Thank you very much, Rob.